So for the series, we're not going to just list the terms. Actually, we are going to add the terms, right? That's how we distinguish a sequence from a sum. When we look at this sigma symbol, that means the sum of all these terms given an algebraic rule, starting at n equals 1 or n equals 2, n equals 3, depending on how we construct the series, like the first term, the second term, the third term, etc., all the way to infinity. Well, this thing about infinity, it's going to give, well, not trouble, I want to say, but I mean, that's actually the whole picture for this chapter, to determine whether a sequence, whether a series converges or diverges. That is, the sum, it's a finite number if possible. In some cases, it's possible to find that sum. Or the sum, it's simply infinity, just in a very similar way that we did for the improper integral. So, well, there's a couple of cases in which we will be able to find an infinite sum. Yes, it's kind of weird to add infinitely many numbers. And that one of those cases is the geometric sequence, the geometric series, and the telescoping series, which we will cover in this section. And well, you cover a little bit of series back in your pre-calculus course, like the arithmetic series, or rather sequences and series and geometric series, and then you added the first 25 terms of the series, the first 1357 terms of the sequence, without listing them and adding them one at a time. No, that's not a feasible task. So you went over some formulas, some theorems to add this number by just knowing the common difference or the common ratio and the total number of terms. So you can get those finite sums in within a minute or two, or even seconds, depending on the complexity. And well, so for infinite series, however, because of the difficulty of finding ways to add these infinite sums, well, in most cases, in the majority of cases, we will just limit to determine whether a series will converge or diverge, all right? And of course, I'm going to make a note in which cases can we find actually that infinite sum. Okay, so here is the big problem that we would have to run into in if we were to find that infinite sum. So, for example, if you consider this series, right? So, which is right here, we can write this as a sequence of partial sums. That is, S sub 1, which just adds the first term. S sub 2, which adds the first and the second term. S sub 3, which adds the first, the second, and the third term. And S sub 4, S sub 5, etc., etc. If it's possible, which is not always the case, if we were able to find a mathematical rule that describes this sequence of partial sums, then we can just find the limit, and that's going to be the infinite sum, the infinite sum of the given series. However, that's not an easy task, and that's again the reason why from this section and on, we will just limit to determine the convergence or divergence. All right, so, and when it comes to finding that sequence of partial sums, that's only possible for now. It's limited only for the telescoping series and the geometric series. We will talk about this in a minute, all right? So, of course, let's have a look at one of those examples in which we would have to do the long way, so you can see how tedious it is and how can this become like harder for other kinds of series. Like, for example, yes, this example is going to take a good minute to go, but still, trust me, it's like the easy example to illustrate this. So let's consider this series and let's expand some of the terms. So I'm going to write, so I'm going to write the sum of these terms. Well, 1 over 2 to the n, starting at n equals 1, we would get 1 over 2 to the n, which is 1 over 2 to the first, that's 1/2, plus 1 over 2 squared, which is 1/4, plus 1 over 8, plus 1 over 16, plus ... Recall that these 3 dots are to indicate that the series goes on forever to infinity. All right? So let's see. Let's consider the sum of partial terms. Okay, so S1. S1 is the sum of the first one term. Well, the only first term is 1/2. Let's define S sub 2. That is the sum of the first 2 terms. In other words, 1/2 plus 1/4. And if we combine these 2 numbers together, we get 3/4. Okay? And then let's see. S sub 3. S sub 3 is the addition of the first, the second, and the third term. Let's list them. Let's write them. 1/2 plus 1/4 plus 1/8. Combining these 3 numbers together will add up to 7 over 8. Let's do one more. S sub 4. That's again 1/2 plus 1/4 plus 1 over 8 plus 1 over 16. And combining those 4 fractions together, and after doing all reductions, LCDs and all that, that's 15 over 16. Okay? So the trick here is to write down a sequence of partial sums given by the following expression. Well, so S of n, which is S1 plus S2 plus S3 plus ... Of course, that one goes on forever. And well, let me do the S sub 4 also, because we already did it as well. So we're going to focus on, let's see, this value right here is this one. This value right here will be this one. This value right there. And one more. This one right here. So let's just write them down. So S of n equals 1/2 plus 3/4 plus 7 over 8 plus 15 over 16. All right, plus etc. Okay. Notice this sum of terms doesn't come from expanding the series. This sum comes from setting up the sum of partial sums, the sequence of partial sums. Well, in the previous section, in the sequences section, we did, coming up with a few terms of the sequence by just plugging in the values of n, 1, 2, and 3, and 4, a few terms, 5 terms, 4 terms, all depending on the question. And then we also did the reverse, which is usually the trickiest part, which is coming up with a rule that represents that sequence of numbers. And for that reason, doing all this, that's what makes the problem hard of finding the infinite sum of every single series. Well, this one is relatively easy to represent. So the question here is, do you spot any interesting pattern of numbers?
The bottom is being multiplied by 2.
Yeah, the bottom are still powers of 2, right? That doesn't change with respect to the original series that we got. All right, let's start with that. And yes, Ricardo? Yes.
I think it's 2n minus 1.
2n minus 1, so
2n plus 1.
2n plus 1, okay, let's see, 2n minus 1. Okay, careful. The n minus 1 on the exponent?
No.
On the expression, right? So yeah, that's a good question. So okay, let's see. Yes, because that is true. Because we have these powers of 2 in the denominator, and the numerators are only one number less than what we have in the denominator. So this should be good. All right. So because in this case, yes, we managed to find a sequence that represents the sum of, or the sequence of partial sums. So in this case, it's possible to find the infinite sum. All right. So in this case, the limit, or rather, the sum, that is the infinite series, equals to the limit as n approaches infinity of 2 to the n minus 1 over 2 to the n. And well, for this limit, we don't even need L'Hopital's rule to simplify. We can split the terms. That's the limit, 2 to the n over 2 to the n. That's 1n minus 1 over 2 to the n. As n approaches infinity, this term goes to 0, and the infinite sum is 1. All right? So again, this small example is relatively easy to compute, but again, other kinds of series like alternating series, like P series, other series that unfortunately this task of coming up with an S sub n, it's not easy. So for this reason, this chapter contains like 9 sections, because we will be studying every single kind of series depending on its form, and all we're going to care is about the divergence or the convergence of the series. Otherwise, if this were an easy task, the textbook would have contained only 2 sections. Number 1 on infinite sequences, and number 2 on infinite series, and we would have been done over here. But that's not the case, unfortunately. So let's have a look at the telescoping series. So a telescoping series is a series of the form b sub 1 minus b sub 2 plus b sub 1 minus b sub 3, etc., etc. So what's interesting about this telescoping series? Well, the thing that is special about it is because, well, this b sub 2 cancelled over here, this b sub 3 is cancelled, and of course many terms get cancelled, and just only 1 or maybe 2 terms manage to survive the cancellation, right? So I guess that's why it's called a telescoping, because your viewer have the telescope. The only thing that you see is, well, all the way to the furthest point that you're on your scope, right? But nothing in between. So it's like it's being cancelled, So let's see. And well, for this type of series, well, in the worst case scenario, we would need to use partial fraction decomposition. So let's see. Let me rewrite this as sigma n equals 1 to infinity. Let me factor n. And well, from here, let's write down the partial fractions. A over n plus b over n plus 1. All right. So let's perform the partial fraction. Remember, we set these two quantities equal to each other. And so that's n times n plus 1. A over n plus b over n plus 1. And recall that we multiply both sides by the least common denominator to simplify the equation, so we can get our constants a and b. Doing the distribution on the left hand side, see how this cancels, leaving us with only the 1. Equals, doing the distribution on the right hand side, see how the n's cancel, leaving us with a times n plus 1. And doing the last distribution on the second term on the right hand side, the n plus 1's cancel, leaving us only with n. And this is again our basic equation. The equation that we will use to find the constants a and b. And of course, think of any convenient values so we can cancel one term. And from there, find one of the constants. Can you think of one of those convenient values?
0.
0 is 1. So n equals to 0. For n equals to 0, that's what is this? Okay, so 1 equals a times 0 plus 1 plus b times 0. And that's going to leave us with a times 1, which is a, equals to 1. All right? Can you think of another convenient value? Negative 1. That cancels the a, zeroes out the a. Negative 1. So that's a 1 equals a times negative 1 plus 1 plus b times negative 1. And in this case we get negative b on the right hand side and a 1 on the left hand side, leaving us with a b equals negative 1. Coming back to the series, so let's see. Sigma n equals 1 to infinity of a, which is 1 over n plus 1, actually minus 1 over n plus 1. And for the telescoping series, what we're going to do is expand for n equals 1, n equals 2, n equals 3, and see how many terms or in which terms actually are the ones that get cancelled. And of course, we'd start on the starting index, in this case n equals to 1. If we had a different index like n equals 2, n equals 2, well, then we would start on that index. So let's start for n equals 1. That'll be 1 over 1 minus 1 over 1 plus 1 plus n equals 2, that's 1 half, plus 1 over 2 plus 1, is that 1? Okay, 2 plus 1 plus n equals to 3, 1 over 3 plus 1 over 3 plus 1. Alright, and we can do this, and see what's going to happen. Well, let me simplify these numbers. This will be, well, so 1 minus 1 half plus 1 half minus 1/3 plus 1/3 minus, actually minus. Do you see what's going on here? So cancel the 1/2, cancel the 1/3, cancel the 1/4, cancel the 1/5, etc., etc. Is there any number that survives the telescope here? That's the infinite sum. That's the infinite sum. Yes?
Could there be a case where no number survives?
The sum is 0.
Okay.
Yep. So yes, I guess whatever would be more time consuming about is a partial fraction decomposition. But not everything is as bad as that. For example, you could be given a series in which the partial fractions are already given, and all we have to do is simply plug in values of n. And in this case, we're going to start with n equals to 1 again. Okay, so let me write down the series first. N equals 1 to infinity. 2n plus 1 minus 2n plus 5. And see, for n equals 1. So 1 over 2 times 1 plus 1 minus 1 over 2 times 1 plus 5. Okay? Plus 1 over 2 times 2 plus 1 minus 1, 2 times 2 plus 5, plus 1 over 2 times 3 plus 5, plus 1 only, minus 1 over 2 times 3 plus 5. And well, let's stop here. If we need more terms, well, we just expanded. Let's start with what we have. So what do we have on the first term? We have a 1 over 2 plus 1, so is that 1/3? And for the second term, inside of the first parenthesis, that's 2 times 1, which is 2 plus 5, that's 1/7. Plus, that's a 1/5, I think. Minus 2 times 2 is 4 plus 5, is that a 1/9? Yes. Let's look at the third group of parentheses. Well, so that's 2 times 3, which is 6 plus 1, that's a 1/7. Oh, do you see what's going on now? Do you see how these terms are going to start canceling? And the next one, that's 2/3. 2 times 3, which is 6 plus 5, 1 over 11. Okay, let me expand one more. 1 over 2 times 4 plus 1 minus 1 over 2 times 4 plus 5, which in this case is 2 times 4, which is 8 plus 1 is 1/9, and 2 times 4, which is 8 plus 5, isn't it 13? And plus dot dot dot. Of course, don't forget that in those 3 dots to denote that the sum goes on forever. So let's see if we can cancel terms now. Okay, can we cancel this 1/7 with negative 1/7? And then it seems like we can cancel the 1/9 with the 1/9, and then eventually we'll be able to cancel the 1 over 11 with the 1 over 11 that gets generated possibly on the next expansion, and then the 1/13. Did you notice which terms managed to survive the cancellation rather? The 1/3 and the 1/5. So in this case, 1/3 plus 1/5 multiply by 3, multiply by 5. So that's 5 plus 3 over 15 and equals 8 over 15. Alright? And that's the infinite sum. This is only one of the 2 cases that we will cover for which it's possible to obtain that infinite sum. Alright? Let's see. What's next? Okay, the next topic is the geometric series, and again, that's something that you have already seen before in your pre-calculus course. Unlike the arithmetic series or sequence, the arithmetic sequence is that sequence of numbers that it's represented by the terms having a common difference, as opposed to the geometric sequence or series that is represented by having a common ratio for every single term. All right. So in this case, what we will do is observe the value of r. That is the number that is raised to the power n. If the absolute value of r it's a number smaller than 1, well, then the series converges, and in that case, it's possible to find the infinite sum which is given by this formula. But otherwise, if that value of r is greater than or even equal to 1, well, then the geometric series is said to diverge and we're done. We don't have to do anything else. Now, need to be careful here. For the geometric series, it must start at n equals to 0. If the geometric series doesn't start at n equals to 0, then we need to rearrange the given series by doing the process called shifting of index, which, well, we will cover that in a few minutes. In the meantime, let's see, we're given a few series, show that the infinite series is a geometric series, and find its sum in the case that it is convergent. All right. So we will be given this this series right here, sigma n equals 0 to infinity of 1 over 4 to the n. Well, so we need to make sure that the given series is represented in the form a times r to the n. That is, a number times another number that is raised to the n power. I don't think this is yet in the correct form. So let's rewrite it first. Sigma n equals 0 to infinity. This is the same as saying 1 over 4 to the n power. And then from here, what we need to do is identify the values a and r. All right? So, let's see. So in this case, okay, let's identify them. That is, a equals to an invisible 1 and r equals to 1/4. So that's the common ratio. All right? So in this case, let's analyze that value of r. So let's take the absolute value of r, which is the absolute value of 1/4. But the absolute value of 1/4 is 1/4. And now here is where the question is 1/4 less than 1 or greater than or equal to 1? Less than 1. So what would you say about this series? Converges or diverges? Converges, all right? So the series converges. And in the convergent case, it's possible to find that infinite sum. All right? So let's see. So find the infinite sum using the formula that we have in here, s with an infinity in the subscript. That's to denote that we are finding the infinite sum. We are not finding the sum of a finite number of terms, like the sum of the first 50 terms, like the sum of the first 117 terms, like what you did in intermediate algebra or in precalculus, college algebra. No, now in this case we're looking for the infinite sum, and that's given by a over 1 minus r, which is in this case a equals to 1 and 1 minus r, which is 1/4. So 1 minus 1/4, what is that?
4/3.
So that's a 4/3. And dividing by 4/3 is the same as multiplying by the reciprocal, which is 3/4. All right? So what does that mean? This means that we are essentially doing the following. So 1/4 to the 0 plus 1/4 to the 1 plus 1/4 squared, 1/4 cubed, 1/4 to the 4th, etc. And that infinite sum equals to 3/4. Yes?
The answer is 4/3.
I see. The
Denominator.
this is supposed to be 3/4, right? Okay, you were giving me the final answer to it. Yes. So 4/3. All right. Well, why are these called geometric series? Well, that's because these kind of series are typically used to model geometric shapes. For example, every time we do an iteration of computing this sum, we are dividing by 4 and then dividing by another 4 and then dividing by another 4, like fractals. Have you heard the term fractals before? So those are like geometric figures that when you zoom it in or you zoom it out, you essentially get the same picture, just bigger or smaller. For example, one case is if we have a square, well, divided by 4, and then divide by 4 and keep dividing by 4, and every time a smaller one. Well, that's not the only possibility. And if you like video games, most likely you will recognize this shape. So that's a division by 4, then divide by 4, and then divide by 4, etc., etc. Right? So that's those are these fractals. So we could have made this even bigger, all right, or smaller. But in the case that we're getting a ratio that is small, that it's a fraction, we're making this smaller in order to convert, to have a sum that converges. Otherwise, the number gets bigger and bigger and just blows up to infinity. All right. So that's one example on on what a geometric series is. How do we determine whether it converges or diverges, and how do we find that infinite sum in the case that the series converges? Because if it diverges, that means it just blows up to infinity. Let's look at letter B. So for letter B, we have the series sigma n equals 0 to infinity of 3 times 5 halves raised to the n power. Well, the good news here is that the given series is written in the desired form, a times some value r that is raised to the n power. Let's identify those values, a and r. In this case, a equals to 3 and r equals to 5 halves. All right? So in this case, we need to observe the value of r. Let's find the absolute value of r. That is the absolute value of 5 halves, which happens to be itself 5 halves. Now the question is 5 halves less than 1 or greater than or equal to 1? Greater than or equal? What does that mean? Converges or diverges? Diverges, and we're done. That's all. Diverges. Okay, shifting indices. So we're going to use this when the given series is not starting at the index, at the initial index that we want. For example, for this particular geometric series, we need to make sure that our series starts at 0. Well, in the following examples, we're going to have series 1 that starts at n equals to 1, and 1 that starts at n equals to 3. And well, so what do we do in those situations? Well, so what we want to do in this case, and well, what I'm going to do on this example is summarize in this definition box right here. So I want to make sure that this is a 0, not a 1. Well, one way to get a 0 there is, well, subtract 1. All right, that's going to give us the 0. However, we need to balance this with the expression that we have in our r over here. So if I subtract a 1 here, then I have to add a 1 in every instance of n that we see on the given series. Well, so 1 minus 1, that's going to be a 0, the 0 that we wanted. N equals 1 to 0 to infinity. That's 5. And well, negative 3/4 to the n times negative 3/4 to the first power. So we're going to use laws of exponents. We are going to rearrange the series just a little bit so we get the desired form. All right, so when we can multiply this 5 with this negative 3/4, that's going to be n equals sigma n equals 0 to infinity. That's negative 15 over 4 times negative 3/4 to the n power. And well, we just rearranged the given infinite series in the desired form. Number 1, a number multiplying another number that is raised to the n power, and which the series starts at n equals to 0. Okay, so number 1, let's write down the a and the n. A equals to negative 15 over 4, and r equals to negative 3/4. So from here we need to analyze the value of r by taking the absolute value of negative 3/4. So now we get one negative value, so that's 3/4. And in this case, well, 3/4 is a number less than 1, not greater than or equal to 1. And for this reason, does the series converge or diverge? Converges. So converges, well, in this case it's possible to find the infinite sum. So, and be careful with the signs here. Those negative signs right here will be actually affecting the value. So you'll see. Or rather, not affecting the value, affecting the way that we will compute that final value. So S sub infinity, A over 1 minus R, where A equals to negative 15 over 4, over 1 minus the value of R, which in this case is negative 3/4. So be careful with the signs here. So, negative 15 over 4. And well, in this case, minus minus, that will turn into a plus. That's a 1 plus 3/4. And well, that's essentially saying 4 over 4. So we can combine the fractions together. And 4 plus 3, is that a 7? So negative 15/4. That's 7 over 4. And well, dividing by a fraction is the same as multiply by the reciprocal. Alright, then just cancel the 4's, and our final sum is negative 15 over 7. And yes, we can get negative values for infinite sums. Alright.